Lesson 11, The Ladder, Part 2. In our previous lesson, we learned the basic mechanics of the ladder. So, in today's lesson, we are going to study a concept that is closely related to the ladder, known as the ladder breaker. What is a ladder breaker? In the last lesson, we already learned that by playing continuous arteries and driving the opponent's stones toward the edge, we can capture those stones. But what if, before we start the Atari, there is already a friendly stone waiting on their path of escape? Will the ladder still be successful then? Let's test this out. When black plays Atari and white tries to escape, we will still try to capture white using a ladder. Now, when we reach this point, as white moves out, we can see that black's ladder has already failed. Next, if black plays Atari here, white can just connect. If black Ataris from this side, white can still connect. And once white connects, it clearly has more than 2 liberties now. Once a ladder fails like this, the consequences are quite severe because it leaves behind multiple double Atari weaknesses. And black simply does not have the time to fix all of these cuts. There is just no way to defend. Therefore, before starting a ladder, we must calculate carefully to see if it actually works. If the ladder does not work, you will pay a very heavy price. Okay, so now we understand the concept of a ladder breaker. Whenever white has a friendly stone in the path, we need to check whether the ladder will still succeed. Now, let me ask you another question. With white's stone placed right here, we know black's ladder will fail. But what if white's stone was placed over here instead? Would black's ladder still work in this case? Well, this is something we need to calculate. And the answer is that it still fails. Let's demonstrate this on the board. As white moves out, black continues to play Atari using the ladder technique. When we reach this point, if black plays Atari from this side and white moves out, notice how this stone acts as a friendly support. As white escapes, this move simultaneously places black's stone in Atari. Now, if black tries to Atari white again, white can simply capture this black stone. And we can see that the ladder has completely failed. Therefore, white's stone in this position still functions as a ladder breaker. But notice what happens if we move white's stone one line further to the right. Now, the ladder will succeed, which means white's ladder breaker is no longer effective. Let's test this out again. Like this. Black is now able to capture white in the ladder. we can see that black's ladder is completely unaffected by that stone. The stone's position is useless here. So this is considered a failed ladder breaker.
All right.
As we mentioned about this white stone, its furthest effective position on the right is here. But what if we place it further to the left? Actually, the furthest effective position for ladder breaker on the left is right here. Let's test this out as well. When white extends and black plays Atari, the result is very similar to what we just saw.
Black cannot Atari here. If black does, white will have 3 liberties.
But if black plays Atari from this side, white's move creates a counter Atari shape. So once again, black's ladder fails. Now let's look at the general rule for ladder breakers. Now we know that when black attempts to capture in a ladder, we must always check if there are any opponent stones acting as a ladder breaker ahead. If there is a potential ladder breaker ahead, we still need to calculate whether that ladder breaker is actually effective. For this, there is actually a simple calculation method. First, through our earlier calculations, we found that for the white stone on the left, this is its furthest effective ladder breaker position. And for the right side, the furthest effective position is here. Once these two outermost positions are determined, we know that if a white stone is on any of the lines between them, the ladder will fail in the exact same way, and white's ladder breaker will be successful. Please note, I am going to introduce a 6-line theory. Here, what does that mean? When white has a stone here, we can extend it. Notice this is one line. Extending upwards, if there is a white stone anywhere here, black's ladder will fail. Notice this is the second line. This is the third line. This is the fourth line. This is the fifth line. And this is the sixth line. Please note that as long as there is a white stone on any of these lines, just one is enough. Then black's ladder will be unsuccessful. I placed all these stones here just to help you understand that white actually has 6 lines that can act as a ladder breaker. 1 line, 2 lines, 3 lines, 4 lines, 5 lines, and 6 lines. And whenever there is a white stone on any of these 6 lines, black's ladder will not work. But if it falls outside these 6 lines, black can capture in a ladder. For example, this position doesn't work. And this position doesn't work either.
With white stones in these 2 positions, black can still capture white in the ladder.
Alright, we've learned the theory, knowing that a white stone on any of these 6 lines prevents a ladder capture. But how should we actually calculate the ladder in a real game? Let me show you a relatively simple method. For example, let's say a ladder forms from a distant position. But white has a stone way up on the board. So how should we calculate this? If we just try to visualize it, imagining playing Atari step by step in our head, it is actually very exhausting because we have to calculate so many moves. So in this situation, we have a method, or rather, two methods to quickly judge if the ladder is favorable. We know that a ladder shape usually travels along a straight diagonal line. So we can quickly project this white stone closer along its line. Because it sits on this exact line, its effect as a ladder breaker remains exactly the same. So when we project this white stone closer to this position, or this one, you will very easily see that your ladder will not work. This is a relatively simple and clear method. Another method involves the black stones. Since we know the direction of the Atari moves like this, you can project the black stones pushing all the way across. For example, reaching this position, we can assume black plays Atari here. White escapes. Black enters again. White escapes again. Black enters again, and white escapes again. Then, when black plays Atari right here, because our stones can also be projected over, all the way across, we project it like this. Up to this position, when playing Atari, and white escapes, the ladder capture will also fail. Both of these methods work perfectly fine. But why teach two different calculation methods? Well, there is definitely a good reason for it. We will explain the reason in our next lesson.